Hello, my friends. So we are at lesson 4, the definite integral and the FTC, the fundamental theorem of calculus. Calculus. Yeah, okay, it's kind of a big deal. So the fundamental theorem of calculus, it's a pretty big deal, but it's actually pretty simple. It's not like a big complicated thing. It's just important to what calculus is. So the fundamental theorem of calculus states that if f, some function, is continuous over the interval ab, where a and b are included on that interval, then there is a function, g of x, let's say, that is equal to the integral from a to x of f of t dt, and that g prime of x is equal to f of x. Very important, x is on that interval as well. Now, if you're reading that and you're like, I have no idea what any of the words that just came out of your mouth mean, Ms. Neufeld, fair. Basically, it's not as complicated as it sounds. All it's saying is that if we're looking at some function that is continuous over a particular interval, then there exists an antiderivative at every point along that interval. Okay, that antiderivative exists for every point between a and b. That's all. So where if I take the derivative of g, I will get f at if I take the derivative of g at point x, I will get the function of f at point x. All right. B states that the integral from a to b over that interval of f of x dx is just equal to the antiderivative at b minus the antiderivative at a, where f is any antiderivative of the original function. So it makes a little bit more sense once you see examples, but the basic premise here is over a continuous interval, every point on that interval has some integral that exists, and that if we want to take the integral over an interval, we just take the antiderivative at the upper limit and subtract the antiderivative at the lower limit. Trust me, once you see some examples, it'll make a lot more sense. Let's talk about some properties, just so we know what we're dealing with. So the integral from a to a of f of x is 0. Well, yeah, that makes sense because I'm not covering any distance. There's nothing there. From a to b of f of x is equal to negative b to a of f of x, integral of f of x, which comes from the exact same premise as this concept that a minus b is equal to negative b minus a. It's the same idea. It's just saying, hey, we just reverse the order, and then we have to factor out a negative. That's all that's happening there. Similar to what we've seen with derivatives, any constant multiplied by the function, we can just take that out of the integral altogether. The sum or difference on the interior of an integral is the same thing as the sum or difference of those integrals. So same as derivatives there. And if we have the integral from a to b of f of x, this is equal to the integral of a to c of f of x plus the integral from c to b of f of x. So if we have some c in between a and b, if we want to get the integral from a to b, we can break it down into pieces from a to c and then from c to b and then just add it all up. This will be useful later. All right, let's try some of these. So first off, we want to determine the integrals, the definite integrals of each of these questions. So we've got the definite integral, sorry, that was not words, the definite integral of x cubed with respect to x from -1 to 2. All right, so with this first one, we're taking the definite integral of x cubed with respect to x from -1 to 2. Okay, to simplify this, I'm actually going to start by just calculating the antiderivative. So for now, I'm just going to figure out what my big f of x is. So I'm just going to take the antiderivative of x cubed. We won't always do this in the future, but for now, start with just the antiderivative. Oh yeah, just fits. So that's going to be 1/4 x to the power of 4 plus some constant, right? Okay, so if I want to find its integral from -1 to 2, all I'm going to do is take that antiderivative at each of those x values and subtract them. So this is going to be equal to 1/4 2 to the power of 4 plus c minus 1/4 negative 1 to the power of 4 plus c. That was a terrible bracket. Bad bracket. All right, well, 2 to the power of 4 is 16. 16 over 4 is just 4. So this is 4 plus c minus, well, negative 1 to the power of 4 is 1 times 1/4 is 1/4. So this is 1/4 plus c. But hey, look what happens here. This becomes 4 plus c minus 1/4 minus c. See what happens to the c's? They cancel out. So all we're left with is 4 minus 1/4, which is 15 over 4. 4 is 16 over 4, so we can write it like that. Now, this is really interesting because that means when we're taking the definite integral, we don't have to worry about including that plus c. So if I'm asking you for the antiderivative or the indefinite integral, you must include that plus c at the end. But for the indefinite integral, we don't have to worry about it because those plus c's, because I'm subtracting, those plus c's will cancel each other out. And we don't have to deal with it. So from now on, I'm not going to include plus c's when doing definite integrals. There's no need to do it. We only have to include plus c for indefinite integrals, for antiderivatives. All right? Let's take a look at b. So we're doing the integral of sine, oh, I changed this one. Sorry. I'm making that 3. Wahaha. Sine 3x dx, I don't know why that deserved an evil laugh, but it did. From pi over 6 to pi over 2. All right, so with this one, I'm going to take my antiderivative, and this time I'm going to use the kind of notation we're going to be using over and over again in this unit. I'm going to be taking the antiderivative, which the antiderivative of sine 3x, if you recall, should be negative cosine of 3x all over 3. And what I'm going to do is I'm going to say that that is from pi over 6 to pi over 2. I'm going to put that on the right side there. Some people don't bother with the opening square bracket. I don't know, I always do. So what I'm saying here is I took the antiderivative, I ignored the constant because I know that since I'm under a locked interval, I meant to say interval, they're two similar words. Since I'm under a locked interval here, a closed interval, I don't really need to worry about the constant because I'm going to be subtracting anyway, so the constant's going to disappear. So I left that off, and then I just did that notation to let me know that I'm taking it from pi over 6 to pi over 2. So what this gives me is this is negative cos of 3 times pi over 2, so 3 pi over 2 all over 3, minus negative cosine of 3 times pi over 6 all over 3. So what this gives me, well, cosine of 3 pi over 2 is 0, and 3 pi over 6 is just pi over 2, so cosine of pi over 2, also 0. So the answer to this one is 0. That's our integral. All right, let's try another example. Let's say we have the integral of sine x with respect to x from pi to 2 pi. So again, I start with my antiderivative without the constant, which in this case is nice and easy. It's negative cosine x. And we're taking that from pi to 2 pi. That means what I'm dealing with here is negative cosine of 2 pi minus negative cosine of pi, which gives me, well, cosine of 2 pi is going to be 1, so this is negative 1, and negative negative is positive, cosine of pi is negative 1, and what I get, negative 1 plus negative 1 is negative 2. So the answer to this integral is negative 2. B. So, first thing I'm going to do is, man, I don't want to deal with this. I haven't taught you guys how to deal with these kind of like chain rule-y integration. Nah. Not worth our time. Let's just expand this guy out. So I'm just going to expand this polynomial. It's a perfect square trinomial, so it's a pretty quick one. There we go. And now it's easy. Now this one's easy to take the derivative. I mean the antiderivative. I can do math. So 4x squared becomes 4x cubed over 3 plus 12x squared over 2 plus 9x over 1 from 1 to 5. So what this means is this is equal to 4 times 5 over 3 plus 4 times 5 cubed over 3, 12 times 5 squared over 2 plus 9 times 5 all over nothing. There was nothing there. I just made something up. There we go. And then we're going to subtract 4 times 1 to the power of 3 over 3 plus 12 times 1 to the power of 2 all over 2 plus 9 times 1. Okay, so what I'm going to do is I'm just going to expand this out. This one's 500 over 3. I trust you guys can do the arithmetic here. Plus 150 minus 45. I'm just expanding. Don't forget to expand your negative. That's a really common mistake. We got to expand our negative into the brackets. So this is negative 4/3 minus 6 minus 9. And I'm just going to jump ahead to the final answer. You can do the simplification, but that's 1036 over 3. So just found a common denominator of 3 and did the basic addition and subtraction from there. I trust that you can do that. And that's our answer. All right. So that one's not too bad. Let's take a look at this guy. All right. We know how to do these. The antiderivative of e to the 2x is e to the 2x over 2. And we're taking that from 0 to 1. So this is going to be e to the 2 times 1 all over 2 minus e to the 2 times 0 all over 2, which gives me 1/2 e squared minus, well, e to the power of 2 times 0 is just e to the power of 0, which is just 1. So this is going to be minus 1/2. Or, if I'd like, I can factor out that 1/2 and make this e squared minus 1. Perfect. Should be highlighting my answers. Make them nice and invisible, especially that one, because he's hiding. All right. Last one in this example. Then another example. So not exactly last one, but you get the idea. So with this one, we're taking the integral from -1 to 3. Nope, I definitely meant to write that. -1 to 3 of, I'm going to rewrite this as x to the -2 dx. Then we take our antiderivative for x to the -2, and that's x to the -1, because we add 1 to that exponent, and then divide by our new exponent, which is -1. And I take that from -1 to 3. So what this gives me is this is going to be negative, because divide by -1 is just going to have a negative up front, 3 to the -1 minus, here we go, more negatives, -1 to the -1. That's a lot of negatives in there. That is a decent number of negatives. So what we get is 3 to the -1 is just 1/3. So this is -1/3. And -1 to the -1 is just going to be 1 over -1. But there's a lot of negatives in here. All 3 of those negatives together is just going to be 1 negative. 1 over 1. And when we finish that off, that just makes it -4/3. There we go. Okay. Final example, example 2. Determine the integral from 0 to pi over 4 of 2x minus secant squared x with respect to x. So I'll do the same thing as we've done in the past. There's really nothing new here at this point. If you know how to take your antiderivatives, you can do the definite integral. So this is going to be 2x squared over 2 minus, well, the antiderivative of secant squared x is tan x from 0 to pi over 4. So what I've got now, the 2's will cancel out, and this just becomes pi over 4 squared minus tan of pi over 4 minus 0 squared minus tan of 0. But pi over 4 squared is just pi squared over 16. Tan of pi over 4 is 1, so this is minus 1. 0 squared, crazy, it's 0. So, you know. And tan of 0, also 0. So what we're finishing with is this is going to be, I'm just getting a common denominator here. This is going to be pi squared minus 16 all over 16. Done. Okay. Finally, with this guy right here. Now, what I'm going to do first is I'm just going to rewrite this guy a little bit before I attempt to do any crazy math with it. So I'm going to rewrite this as t squared over t plus t to the 1/2 over t minus 2 over t dt. And what this lets me do is it lets me turn this thing into just a bunch of terms, which makes taking the derivative a whole lot easier. Instead of having to deal with some kind of reverse quotient rule business here. Now, we're not dealing with that right now. We're just going to go ahead and make this as simple as we can. And I always recommend, if you can make your integral simpler before you actually integrate, you should do that. Make it simple. T to the 1/2 divided by t is just t to the negative 1/2. And obviously this is just equal to 2t to the negative 1. Now this one's not so bad. Now we can take our antiderivative of all of these terms. So this is going to become t squared over 2 plus t to the, oops, that's supposed to be a negative 1/2. Haha. T to the 1/2 all over 1/2 plus minus, now remember, we can't just add the exponent here, so this is going to be natural log of t from 1 to 4. So what I got here now is this is going to be 1/2 4 squared plus, that divided by 1/2 just becomes 2. 2 times 4 to the 1/2 minus 2 natural log of 4 minus all the same stuff but with a 1. 1/4, 1 squared, plus 2 times 1 to the 1/2, minus 2 natural log of 1. All right, so I finished this off. We have 4 squared is 16, 1/2 of that is 8. 4 to the power of 1/2 is 2, times 2 is 4. 2 natural log of 4 is 2 natural log of 4, I don't know what that is, minus 1/2 times 1 squared is just 1/2. 2 times 1 to the 1/2 is just 2, so minus 2. And then 2 to the 2 times natural log of 1. Well, natural log of 1, don't forget, is 0, right? So natural log of 1 is equal to 0. That's because the log of anything, log of 1 is always 0, no matter what the base is. Because the only way to get 1 as your answer is if our exponent is 0, right? So because of that, we can just say that this is just minus 2 times 0. So to finish this up, we combine all of our little numbers there, and we get 19 over 2, that's 8 plus 4 minus 1/2, minus 2 natural log of 4. Ta-da! Go do your homework. Bye.
Hello everyone, this is Italics coming from the future. I just wanted to point out that my silly human didn't fully simplify her logarithm. But through the power of time travel and video editing, you can see the way to simplify it correctly on the screen in front of you. I will meow at her incessantly until she fixes her notes. Cheer meow!